Picture a table of student records: roll number, name, date of birth, phone. A couple of different things can pin down a single row. The roll number alone works, but so does the bundle of name, date of birth, and phone together. Both feel like keys. Which attribute sets truly qualify? Are there others we haven't spotted? And can we find every one of them mechanically, using only the functional dependencies, without ever peeking at the actual data? By the end of this lesson, you'll have a precise algorithm that does exactly that and turns guessing into a checklist. First, the bridge from the last idea: attribute closure. Remember, the closure of a set X, written X plus, is every attribute X forces to be determined. That single tool gives us both words we need. X is a superkey exactly when its closure is all the attributes of R. It determines the entire row. And a candidate key is a minimal superkey. Minimal means you cannot throw away a single attribute and still have a superkey. Drop anything, and the closure stops reaching everything. So a table can have many superkeys. Just pile on extra columns, but only a handful of lean, minimal ones underneath. So finding candidate keys becomes one clean job. Find the smallest attribute sets whose closure is the whole relation. Every candidate key is a minimal such set. Testing every subset of attributes would be exponential. But there is a beautiful shortcut. Just look at where each attribute appears in the dependencies: on the left, on the right, or both. First group, call it M. Attributes that appear on no right-hand side at all. Nothing can ever derive them, so every candidate key is forced to contain all of them. Second group, N attributes that show up on the right, but never on the left. They are always determined by others, so putting one in a key only bloats it. No candidate key ever contains them. And the rest? O, attributes living on both sides. These can determine and be determined. So suitable pieces of O added onto M are what round out our keys. Every attribute lands in exactly one of these three buckets. That single sorting step shrinks the search from hopeless to easy. Here's why that matters so much. Checking every possible subset of attributes is 2 to the n work. It explodes. But the shortcut fixes most of the answer for free. M is forced in, N is forced out, and only the both sides group is left to decide. You search a tiny space, not a giant one. Here is the whole recipe. Step 1. Sort every attribute into Mn or O, the way we just did. Step 2. Start with k equal to m, the mandatory attributes, and compute its closure. Step 3. If that closure is already everything, you're done. M is the one and only candidate key, because any larger set would fail to be minimal. Step 4. Otherwise, grow k by pulling in attributes of O. Try adding one at a time, and if no single one finishes the job, try pairs, then triples. Step 5. Keep a set as a candidate key only when its closure is all attributes, and every proper subset falls short. And once a key is found, never bother testing a bigger set that contains it. A superset of a key can never itself be minimal, so it's wasted effort. That's it. Let's watch it run on real schemas. First schema. R has 5 attributes and 3 rules. A determines B, B and C together determine D, and D determines E. Let's find every candidate key. Step 1. Classify. A is only ever on the left, so A goes in M. B sits on both sides, so B is in O. C, like A, is left only into M. D is on both sides, O. And E appears only on the right, so E lands in N. Collect the buckets. M is A and C. N is just E. N is just E. O is B and D. So every candidate key must contain A and C and can never contain E. Step 2. Test M itself. Take the closure of A and C. Start with A and C. A gives B, so now A, B, C. B and C together give D, add D. And D gives E. We've reached all 5 attributes. So A to C is a super key. Is it minimal? Drop C and close A alone. A gives B, and then B to C can't fire without C. So A stalls at AB. Drop A and close C alone. Nothing fires, just C. Neither half reaches everything. So A to C is minimal. It's a candidate key. And because M itself already closes to everything, no other set can be minimal. A to C is the one and only candidate key of this relation. A trickier one, where more than one key hides, are with 4 attributes and the rules. A gives B, C gives D, and B and C together give A. Watch the shortcut do the heavy lifting. Classify first. A is on both sides, so OB is on both sides. OC sits on the left twice and never on the right, into M. And D is right only, so N. C must be in every key, D in none. So we start from C and reach for pieces of O. Close C by itself first. C gives D. But that's all, just C and D. Not a super key. So C alone won't do. Add a closer and C. A gives B, so A, B, C. Then C gives D, and we hit all 4. And its halves each fall short. A plus is AB, and C plus is CD. So A to C is a candidate key. Now try B instead. Close B and C. B and C together give A. So A, B, C. Then C gives D, all 4 again. B plus is only B. C plus is C and D. So B to C is a candidate key too. To candidate keys, then, A to C and B to C. Notice C sits in both, exactly because it's on no right-hand side. And beware, A, B and C together do close to A, B, C. But that misses D, so it isn't even a super key. Once the keys are in hand, we label the attributes one final way. A label the next lesson leans on heavily. Take our second relation, whose keys were A to C and B to C. A, B, and C each belong to at least one key. So all 3 are prime. D belongs to no key. So D is the lone non-prime attribute. Prime versus non-prime is precisely the language normalization speaks. The rules that decide whether a schema is well-designed are stated entirely in terms of which attributes are prime. So getting the candidate keys right is what makes that whole classification trustworthy. Your turn. A small relation, R of A, B, C, with a gives B and B gives C. Pause the video now. Find the candidate key and say which attributes are prime. I'll wait. Here's the walkthrough. Classify A is left only, so it's in M. B is on both sides, O. C is right only, so N. M is just A. Now close M. A gives B, then B gives C, so A alone closes to A, B, C, the whole relation. M itself is a super key, so A is the unique candidate key. So A is prime, and B and C are non-prime. If you got that, you've genuinely mastered the method. Trap 1. Forgetting the mandatory attributes. If an attribute is on no right-hand side, including one that appears in no dependency at all, it must be in every candidate key. These are the easiest to miss. Trap 2. Smuggling in a determined attribute. Anything that's on the right but never the left is always derived. So it belongs in no candidate key. It can only bloat a set. Trap 3. Skipping minimality. Showing a closure equals everything only proves you have a super key. You must still check that every proper subset falls short. Trap 4. Stopping too early. Unless M alone was already a super key, one candidate key does not mean there's only one. Keep testing the other combinations. Let's lock it in. A super key has a closure of everything. A candidate key is a minimal super key, the smallest set that still determines the whole row. The shortcut. Attributes on no right-hand side sit in every key. Attributes on no left-hand side sit in none. So build up from those mandatory attributes. Add pieces of the both sides group, and keep only the minimal sets whose closure is all attributes. Finally, mark each attribute prime if it's in some key, non-prime if it's in none, the exact language you'll carry straight into normalization. Master these 4 lines, and finding candidate keys turns from the trickiest topic in databases into something you do almost on autopilot.